Okay, good afternoon, everybody over there. My name is Kristjan Pilt. I'm from Department of Health Technologies from Tallinn University of Technology. I work as a senior research scientist in here. And also, I would like to thank also Professor Augustinjak for the invitation to give this presentation in your seminar. We met with him. Met with him in May in last year in Kaunas, and we were discussing also some possibilities perhaps in the future for the collaborations. So this might be this presentation might be perhaps the first step in this direction. So I have given very broad title to this presentation, and it will consist mainly overview of the research that is related to the photoplethysmography and mental stress assessment. However, in the beginning of this presentation, I'll also give a short introduction of where I come from and about our research group, like other topic, which is very important as well for us. And then I'll talk about photoplethysmography and the research that I've been involved during last years. And in case I will have time, I'll talk in the end also about the project that we carried out to estimate the well-being of the citizens in the city environment. So, as I told before, I'm from Estonia. I'm from Tallinn. I work in Tallinn University of Technology, which is the campus-style university and can be seen on this nice picture. So we are located about 6 kilometers from the center of Tallinn, next to the Pine Tree Park, and all of our schools are located in the same campus, which makes the communication between the different institutes and the departments quite comfortable. Here is given the structure of our university. So apart from the administrative part, which is the upper part of this figure, we have 4 schools which are given in the blue. Just a moment, I'll also take the laser pointer. Yes, so School of Engineering, School of Information Technologies, School of Sciences, School of Business and Governance, and we have also Estonian Maritime Academy. So our department is the Department of Health Technologies, and we are under the School of Information Technologies. Nevertheless, as the medical technology is like the interdisciplinary area, then the applied research that is partly related to the biomedical engineering can be found as well from the other departments. For example, we have group in the mechanical and industrial engineering. So they are dealing with the printing of prostheses, for example. The Department of Health Technologies combines the biomedical engineering and digital health competencies, and we serve the public sector as well the private sector. And we have very close cooperation with North Estonia Regional Hospital, which is the largest hospital in Estonia. So we have in our department as well the doctors who are teaching master level students in anatomy and physiology, for example, and as well they are involved to work of our research groups, and also therefore some of the doctors are as well the PhD students in our department. And from private sector, we have a very good collaboration with Karl Storz, who is developing and producing video endoscopes in Estonia. And we also do teaching. So we offer master level medical technology and physics program, which is in Estonian. And there is also master program in digital health, which is given in English. So we have quite small groups for master courses. We have entrance about 25 students. It's quite a small number, but also our department is quite small. We have about like 50 full-time academics and administrative workers, and it includes as well the PhDs. So in our department, we have 4 research groups, which are under the Center of Biomedical Engineering, Biosignal Processing Laboratory, Center for Cardiovascular Medicine, and Center for Digital Health. So, yeah, Biosignal Processing Laboratory is dealing mainly with the EEG signal recording and then processing. Center for Cardiovascular Medicine is more to the medical side. They are studying the personalized approaches for the atherosclerosis prevention, and Center for Digital Health is dealing with the e-health problems. So I'm from the Center of Biomedical Engineering, and historically, this research group has been making the research in the area of real-time monitoring of uremic toxins removal during dialysis treatment. So patients with kidney failure needs to have weekly dialysis treatments. And during the treatment procedure, the toxins are removed from the blood using the filter, and those toxins are guided then to the drain of the hemodialysis machine. So in order to improve the dialysis treatment efficiency and the survival of the patient, there is need to monitor in online the removed toxins during the dialysis procedure. And as a result of the decades-long research, I would say, by Professor Ivo Fridolin, the first prototypes of the optical sensors have been developed, and also they have already tested in the dialysis centers in Europe that enable, and they have shown that this optical sensor enables the monitoring of the removed toxins in the spent dialysis. So the optical sensor is placed to the drain of the hemodialysis machine, and the spent dialysis passes through it, and the sensor measures the light absorption and fluorescence and different wavelengths in the UV region. And based on the multi-wavelength models, the removal of the certain toxins can be monitored in such a way. So about 10 years ago, our research group was expanding, and new topics came on table, which are related to the development of algorithms for the physical activity detection, energy expenditure, and stress estimation. So this expanding occurred mainly due to the successful project fundings in those areas. So we do for what we get money for, and then I think it's nowadays the main driving force. So mine and also partially our research group driving force in the improvement of human health and well-being has been long in the area of cardiovascular disease prevention. So according to the WHO, the cardiovascular diseases are the leading cause of death globally. And atherosclerosis is the endovascular inflammatory disease, which increases the stiffness of the arteries in the beginning of the disease, and it results in a build-up of plaque in the wall of artery, which may block the blood flow and therefore cause, for example, the stroke or heart attack. So in case arteriosclerosis is detected in the early stadium by the doctors, then the progression of the disease could be stopped by right treatment, or the patients could be advised to change their lifestyle, for example. So do we want or not? But during the healthy aging, the stiffness of our arteries is increased. So this is called healthy aging. And mostly the increase in the arterial stiffness depends on our lifestyle, whether we are smoking or dealing with fitness or different physical activities. So the increase in the stiffness can be different in this way. So during the propagation of the arteriosclerosis, the stiffening of the arteries is like accelerated. So it gets stiffer in the time more quickly than during the healthy aging. So it is good if we detect this arteriosclerosis in the early stadium. And for example, in case we visit our family doctor, in addition to the blood pressure measurement, it would be also good to have some very simple device that may detect the stiffness of our arteries in the similar manner as they are measuring the blood pressure. So this kind of method should be therefore very simple to carry out. There is no need for operator. It's rapid. It should be inexpensive. So over the years, there have been developed different methods for the local, regional, and the systemic arterial stiffness estimation. So the local arterial stiffness measurement can be based on, for example, ultrasound measurement, where the diameter or the volume change of the artery due to the blood pressure change in the artery is measured, and based on the measured parameters, the compliance or the distensibility of the artery is calculated. So this measurement is carried out on the specific location on the artery and only for this specific location. As well, in case the thickness of the arterial wall is measured with the ultrasound, then also the Young's modulus can be calculated from those measured parameters. However, this method definitely needs trained operator, and as well the methodology is quite complex, as synchronously with the ultrasound measurement, also the blood pressure measurement has to be carried out simultaneously, and this might not be the very good option for this kind of easy and rapid arterial stiffness estimation method. So then there is regional arterial stiffness estimation methods. So this regional arterial stiffness is estimated either for the one segment of the artery or the segments of the artery. So often in clinical practice, the carotid femoral artery pulse wave velocity is measured for that reason. So the pulse wave that is generated by the heart travels through the arteries with a speed that is among other parameters determined by the stiffness of the arteries. So the other parameters are, for example, the density of the blood, but the stiffness of the arteries determines the pulse wave velocity. And the more stiffer the artery, the faster is the pulse wave velocity in the artery. And for this pulse wave velocity measurement, the pulse wave is measured from the 2 points on the arterial tree. For example, those two locations. and it is recorded using for example, the piezoelectric sensor. And then the time difference is between the arrival of the two pulse waves is calculated, and the distance between the two signal measurement points are measured. So it's telltale, and as a result, we can calculate then the velocity of the pulse wave. And the third is the systemic arterial stiffness estimation, which is based on the pulse waveform analysis. So the changes in the pulse waveform are dependent on the stiffness of the arteries. For the systemic arterial stiffness estimation, the pulse wave needs to be measured from the artery using, for example, the piezoelectric or optical sensor. So we have used in our research the photoplethysmographic method for the pulse wave registration. So photoplethysmography, or shortly the PPG, is a non-invasive optical method that registers the relative blood volume changes in the arteries and microvascular bed of tissue. So most probably you might have noticed that this method has gained quite a lot of attention during last 10 years. And this technique has been, for example, integrated to the smartwatches for the heart rate and blood pressure estimation. Also, the SpO2 measurement is based on this PPG method. And for the PPG signal registration, either the transmission mode or reflectance mode sensor can be used. So in case of the transmission mode sensor, the LED and the photodetector are placed opposite sides of the measured volume, and the light intensity changes through the finger are related to the volume change of the blood. So this is like the very simple explanation of this method. So similarly, the LED and photodetector can be placed adjacent to each other, and then the backscattered light intensity changes that are detected with a photodetector are related to the blood volume changes in the measured volume. So due to the simplicity of this sensor and also to this method, it is relatively inexpensive. Also, the PPG signal can be measured without trained operator. It's quite simple. So the example of the registered PPG signal is, or the PPG signal pulsatile component is given in here on this figure. And this pulsatile component is related to the cardiac cycle, and it is generally accepted that it can be taken as the pulse wave that is generated by the heart. And we can see this waveform is the light intensity changes waveform. So this means that where the light intensity is minimal, then the absorption of the light is maximal. So this is like systole, where in the finger there is maximal volume of the blood, and here is the light intensity is maximal. So this means that there is minimal volume of the blood in the finger. So often this pulse wave is inverted. So it looks like something like this, as it is given in those figures. So it is like inverted. So it is related then with a waveform itself. It is related, and it is related to the volume change of the blood, or also it is similar to the pressure waveform. The pulse waveform changes with the aging of the arteries, which is illustrated on this figure in here. We can see how the curvy signal, which is visible usually in young subjects, it turns to the like triangular sawtooth signal. So it's more visible in old subjects in case they have like increased they their arteries are with increased stiffness. So different methods can be used to analyze this waveform changes that are caused by the arterial stiffness. And lately, there has been also published a review of the usage of PPG method for the estimation of arterial stiffness and related vascular aging. So there has been carried out a lot of research as the PPG method and this technique has potential for this screening device for vascular aging estimation. And there are different arterial stiffness and vascular aging related parameters that are calculated either from the single or from the multiple PPGs. Also, the other signals are combined with a PPG signal for that purposes. So our effort in this PPG waveform analysis has been related to the systemic arterial stiffness estimation and aortic augmentation index assessment. We have developed algorithm for the aortic augmentation index estimation using the PPG signal waveform. So the aortic augmentation index, that is also clinically used parameter for the systemic arterial stiffness estimation, is the ratio of the augmentation pressure. So it's denoted here with a AP to the pulse pressure, denoted as a PP here. And it is the waveform, pressure waveform is also visible in here. So here is the systole, here is the necrotic notch, and so this is the recorded pulse waveform. And this pulse waveform is recorded from the radial artery by placing a sensitive piezoelectric sensor to the skin, and by applying a small pressure to the artery, the radial artery pulse waveform can be recorded. So thereafter, the signal is registered from the radial artery. It is the generalized transfer function is used, and the aortic pulse waveform is then calculated, and from this aortic pressure waveform, the augmentation index is calculated. So the device called Spimacor is widely used for this augmentation index estimation, and however, nowadays there are also other similar devices already available, but as you can see, this method needs the operator who is placing the piezoelectric sensor to the radial artery. So this method needs definitely the trained operator to carry out the measurement. So we had a question that can we use the PPG signal waveform analysis for the aortic augmentation index estimation, because the PPG technique is simple and also inexpensive, and we can basically continuously measure the pulse wave from the finger, for example. And therefore, we developed the algorithm for the pulse waveform analysis, and we carried out the study for that. So we had 20 healthy control subjects and 21 diabetes patients. We placed the subjects to the supine position. We recorded during 1 minute the PPG signals from the finger, and thereafter we used the Spimacor device for the aortic augmentation index estimation. We made 3 consequent measurements for that. And then we developed the PPG signal waveform analysis algorithm that also takes into account the changes in the heart rate. So we limited for each period of the PPG signal, each cardiac cycle period, we limited the harmonic components of each period to the 6. So each period, each PPG signal period consisted of the 6 harmonic components. And then we took the second derivative signal from this waveform and also the fourth derivative from this PPG signal waveform. And then we detected from the second derivative signal waveform the distinct peaks. They are denoted as A, B, C, and D usually. And from the locations of the B and D, we took the amplitudes of the PPG signal, and then we took the ratio of those two amplitudes. So this is similar to the aortic augmentation index waveform analysis. However, we did some signal processing addition to that, and then limited the harmonic components to the 6 harmonic components only. So we could see that the PPG AI index, so augmentation index that is calculated from the PPG signal, and the aortic augmentation index that is calculated from the with a device of the Spimokor, they are related to each other. And also in case of the diabetes patients who have the increased arterial stiffness, so they and we could see from the results that diabetes patients had higher augmentation index and also the higher PPG AI index. So we could see that this PPG AI index could work for the estimation of the aortic augmentation index and the estimation of the detection of the increased arterial stiffness. So when we are measuring the PPG signal, then usually the spot where it is very simple to measure the PPG signal is the finger. So, and during the measurement of the PPG signal, we want or not, but the PPG sensor applies certain amount of contact pressure to the finger and as well to the artery. So in case the pressure is too high, the arteries are then closed and there is like minimal amount of pulsation in the signal or no pulsation at all. And in the other side or the other hand, in case the contact pressure is too low, then the PPG signal is the noise signal to noise ratio of the PPG signal is therefore low. So if the contact pressure of the sensor is low, so therefore there exists most probably an optimum for the PPG signal registration for the PPG AI index measurement. So and it is more uniform to use instead of the sensor contact pressure, the transmural pressure, as it is also depend on the arterial pressure, which exerts counter pressure to the sensor contact pressure. So, and the transmural pressure is then the difference between the arterial and the sensor contact pressure. So we take into account, in addition to the sensor contact pressure as well, the arterial pressure. So it is more uniform to use this kind of this parameter. So, and we then try to find the answer, like what could be the good contact pressure for the PPG index determination. So we carried out again the study on the 51 healthy subjects. We constructed the experimental setup that can be seen in here. So we connected two PPG sensors to the fingers. So those are basically the phenometer device sensors. So they include the photodiode in one side and LED in the other side, and it has the cuff. So the cuff is wrapped around the finger, and we can increase the pressure inside the cuff to change the pressure of the contact pressure of this sensor. And also we measure the blood pressure signal synchronously, and we also measure the aortic augmentation index using the Spimokor device. So we increased the cuff pressure between the certain pressures, 20 to 100 millimeters of mercury, and we recorded the PPG signals at those pressures. And we can see that the PPG AI index depends on the transmural pressure. So transmural pressure is in the x-axis and PPG index is in the y-axis, and we can see that the PPG AI index is stable until near to the mean arterial pressure, or where the transmural pressure is zero, and then the PPG AI index starts to decrease. We can see as well how the PPG waveform changes, how it is stable in the beginning, and then when the contact pressure is increasing or the transmural pressure is decreasing, also the PPG signal waveform starts to change. So we also tried to find optimal transmural pressure for the PPG signal registration and the PPG AI index determination. So we used the standard deviation of the PPG AI index and also the correlation between the aortic augmentation index measured with a Spumacor device and the PPG AI index. So if we found that the maximal correlation was found around between the aortic augmentation index and PPG AI index was around 20 millimeters of mercury of the transmural pressure, and the standard deviation of this PPG AI index was minimal at around 10 millimeters of mercury of transmural pressure. So we could say that the optimal transmural pressure is at around 10 millimeters of mercury or like 20 millimeters of mercury. And we also draw the relationships between the PPG AI index and the aortic augmentation index for those two transmural pressures. And the dotted line expresses the relationship from our previous study that I was showing some slides ago in here. So this is the dotted line on those figures. So we can see that on those two transmural pressures, the results are quite nicely aligned. So the contact pressure of the sensor therefore should be selected according to the finger mean blood pressure of the subject for the PPG AI index and arterial stiffness assessment. And as well, we can debate that perhaps the transmural pressure might affect as well the other waveform parameters used for the estimation of the arterial stiffness or blood pressure. For example, the blood pressure is also estimated in the smartwatches, and in case it is based on the waveform PPG signal waveform analysis, then also perhaps the transmural pressure should be taken into account in such applications. So this was about the arterial stiffness studies that we have carried out previously, and our attention has been in recent studies on mental stress. So we want to use the PPG AI index, which is related to the arterial stiffness. And as the arterial stiffness is increased due to the mental stress, then we have tried to find the possibilities how to detect the increase in mental stress using this PPG AI index, and as well other parameters that can be calculated from the PPG waveform. So the mental stress is increased in our nowadays fast changing society, and this increased mental stress may cause the health problems to us. So in case we can detect the stressful moments using the objective tools for that, then they might notice us and give a notice to us, and we might then apply some relaxation maneuvers, and this may in the end prevent the anxiety and depression, for example. So the physiological response to the stressful situation is quite complex, but simply speaking, the brain is basically producing or releasing the stress hormones, and which in the end causes, for example, the increase in the heart rate, in the breathing rate, in blood pressure, and skin humidity, and as well in the arterial stiffness. So unfortunately, none of those given physiological reactions are stress specific. So therefore, the combination of these physiological signals could provide perhaps the objective assessment for the mental stress. So particularly in our studies, we have been interested to assess the increase in the arterial stiffness to this increase in the acute mental stress, and to combine these parameters with the other physiological parameters. So the PPG waveform indices have been also studied in previous studies, how those waveform parameters are related to the mental stress, and they have been numerically modeled, and also changes in the amplitude of the PPG signals, and as well the time intervals between those wave peaks have been associated with a induced mental stress in laboratory. So we also tried to characterize the changes in the finger PPG signal using the PPG parameters, PPG waveform parameters, and as well the second derivative PPG signal parameters. So we developed, based on our previous understanding of the contact pressure and how the contact pressure affects the PPG signal waveform. So we constructed the PPG finger sensor that works in transmission mode. So we have in one side the LED, and the other side we have the photodiodes, and this is how the finger is placed between those two sides. And also in the under here we have the force sensor that measures the applied force to the finger, so we can place the sensor to the finger with the right contact pressure. So in this study, we extracted from the PPG signal different parameters that, for example, the PPG AI index, and as well the slope of the raising front of the PPG signal, and as well the second derivative signal amplitude ratios, which are quite often also used in the literature. So our experiment included 31 subjects. We asked them to be in the beginning with the closed eyes for 3 minutes. Then we asked them to open the eyes for 4 minutes, and then we asked them to carry out the serial sevens test. So this means that we gave them number between 90 and 100 and asked them to start to subtract the sevens from each number. And we could see that the PPG signals were quite unchanged during the eyes open and eyes closed state, but during the stress test we can see noticeable changes in the waveform. And we carried out also the statistical analysis. We used a non-parametric Wilcoxon rank sum test to investigate the statistically significant differences between those with those parameters and between those three different states. So it's the eyes closed state, eyes open state, and stress test. And we could detect the certain waveform parameters that seems to be valid to include to the model for the mental stress estimation. So in order to increase the estimation accuracy of the mental stress. So then we went with this method to the out from the laboratory. We wanted to see whether this mental stress estimation would work also outside from laboratory, for example, in the outside. And we faced with a problem, which I was not in the beginning. I knew that this problem might come up, but I thought that we can avoid it. And the problem is the temperature problem, because if we enter to the cold environment and the vasoconstriction occurs in the finger, and also the skin perfusion drops because of that, and this lowers the PPG signal amplitude and also the signal to noise ratio. So even we try to wear different gloves on the hand, but still, if outside temperature was 9 degrees, then we can see like how the PPG signal looked like. So therefore, we tried to find another location for such occasions, and we found that the forehead is less affected by the external temperature changes compared to other peripheral locations. Of course, the forehead PPG signal waveform, which is given in this figure in the blue, it differs from the finger PPG signal waveform. So, and it is due to the fact that the arterial trees from the heart to the finger and from the heart to the forehead are, of course, different, and therefore also the waveforms are different. So we wanted to know whether from the forehead registered PPG waveform can be used instead of the finger PPG waveform for the stress assessment using this PPG AI index. And also for that we carried out a study. So we constructed the forehead PPG sensor. So it is based on the fully integrated analog front end AFA 4490 chip from Texas Instruments. You might be also familiar with this because it's quite often used in these PPG sensors. And we used the shielded reflectance mode forehead PPG sensor. So it has one photodetector in the center and then 4 LEDs in the infrared region around this photodiode. And the distance between the LED and photodiode of each photodiode was 8 millimeters. And we attached this sensor to the forehead using this silicon holder. So we registered the PPG signals from the finger and from the forehead synchronously. And we carried out this pilot study on the 16 healthy subjects. And we asked the subject to be in the sitting position with open eyes in the quiet room for 4 minutes, and thereafter we asked them to carry out the stress test. And we used 3 different stress tests: Stroop test, trail making test, and serial 7's test. And then we recorded the PPG signals. And we can see that there are differences in the waveforms from the finger and from forehead. And there are also differences between the rest state, it's given with the blue line, and between the stress state given with this red line. And we could see that there is statistically significant differences between the stress and rest states in this PPG AI parameter. And we can see that in case of the finger, the PPG AI index values are lower, and in case of the forehead, the values are higher due to the different morphology of the finger and forehead signals. However, in both cases, we can see that there is a statistically significant difference between those two states. So we also place to the, like, how to say, ideally, the finger PPGAI index and then forehead measured PPGAI index, they should behave in a similar manner in the rest state. So we plotted the results to the same graph, and we can see that they are related quite strongly and linearly. However, in case of the stress state, we can see that there is no linear relationship between those two parameters, even though they are representing the same. Even though they are the same parameter, but they are detected from the two different locations from the body. So this means that the arterial tree reacts to the stress most probably differently. So we can say that the forehead and finger PPG signals are not interchangeable and in a stress assessment. So, but we can perhaps use this forehead PPGAI index for the stress detection. So now I come to the last topic, what I would like to share with you, and it is related to the well-being score and to the project that we carried out a couple of years ago, and we applied our PPG knowledge for the stress assessment as well in this project. So the project, the well-being score project, was aimed to objectively estimate the well-being of the subjects in the different urban environments. So the aim of this project was to develop like an objective tool that may help, for example, city planners to make like better decisions. So city planners have to make quite often expensive decisions because they are creating the environment where the citizens later on have to live, and also perhaps sometimes have to suffer. So it is better to make the good decisions and the money is spent then in the right direction. So and this well-being score included the assessment of the public urban spaces based on the spatial characteristics, as well as the physiological and psychological responses of the citizens. So therefore, we had also in this project in our team also the landscape architects and also the environment psychologists. So our project was trying to make an attempt to answer like the questions: how do city residents perceive urban space physiologically? So we have two spaces, but how the residents feel themselves physiologically in those environments, and could this be related to the characteristics of the urban space? So the well-being score project was carried out in Narva. So here is the Estonia, here is the capital Tallinn, and we have Narva, which is in the border of the Russia. So this is the border city. And at that time, when we started to make this project, this Narva. The number of the citizens in Narva, they have there right now about 65,000 people, but they estimate that within next 10 years, the number of the citizens in this city will decrease to about 50,000. So they have to, the city architects, they have to start to make decisions where to put the money, which locations in the city to develop and which to leave leave out from this funding and development. So we carried out this measurements and this well-being score development in the Narva, and we measured like the physiological parameters from the subjects, and as well they filled also some psychological questionnaires, and also the landscape architects estimated the parameters of the urban environments. So how much there are pedestrian streets in these locations, how much there is grass, how much there is points of interest, how much there is there are trees, and so on. So we had like complex of the urban space parameters, physiological parameters, and psychological parameters. And we firstly carried out this pilot study on the 28 subjects from Narva to see whether we can detect any changes between the urban spaces. Like, can we see any changes in the physiological parameters if you place the subject in one location, which is which has noise and traffic, and the other location is in the next to the river, which is nice and quiet place? Can we see any differences between the in the parameters of the physiological signals? And as a result, yes, we could see the changes there. And then thereafter, we carried out the larger study on the subjects from Narva, and we estimated then the psychological and physiological parameters in those 6 different living districts in Narva. So we can see that they are quite similar, more or less, if you are looking at them. And we placed the subjects with the sensors to those locations, to the same viewpoint, so they all looked the same view every time when we brought the subjects there. And they answered to the psychological questionnaires, like how they feel there, what is the historical connection to this place, and etc. And we monitored and recorded the different physiological signals. So we recorded the electroencephalogram, the photoplethysmographic signal from the forehead, in order to derive the arterial stiffness related parameters. We had also the skin conductance measurement from the finger, and also we registered the temperature from the cheek and from the finger. So the subject looked like something like this when they went to the city with us to make the measurements. And we had the study protocol that included as well the sitting in a quiet room with eyes closed, eyes open. This was for the purposes of the EEG, the brainwave signal analysis. And then they answered to the psychological questionnaires, and then we carried also out the stress test in order to understand what is the maximal stress level, maximal possible stress level in this location. And then we had recorded the signals, different signals: ECG, PPG, cheek temperature, skin resistance, and also the EEG signals. And we made the signal processing of those signals, and then we calculated the heart rate variability related parameters, the RM, SST, and STNN, which is quite known heart rate variability parameters. We calculate arterial stiffness parameters from the forehead PPG signal. We use the cheek temperature signal and also the pulse transit time signal. So pulse transit time is the time delay between the ECG signal R peak and the delay between the when the pulse wave arrives to the forehead. So this is related. The pulse transit time is related to the blood pressure. In the other words, so if the blood pressure increases due to the stress, then the pulse transit time decreases, as it is in here. And also we calculated our EEG group calculated the brain activity related parameters. And so we had the results of the physiological measurements. So we could assess we calculated based on those parameters in here, and based on the difference of the observational and the stress test state, we calculated the parameter that we scaled to between the 0 and 100, and we said that it is the well-being score of the subject. So in the other words, it is like stress score if we take the reciprocal of this value. So the higher the score, the lower is the stress level, and the lower is the score, the higher is the stress level in the other words. So we turned it upside down. We wanted to say that we are measuring well-being, not the stress of the subject. So we want to be like a positive. And we can see that we could find a statistically significant differences between the urban environments that I was showing in the previous slides, where the subject was sitting in those locations. And those are the values or the differences what we found using the parameters from the brain signals, from the EEG signal. And quite similar results we could find also in case we merge together the other signals, the cardiovascular signals, and also the cheek temperature. So we could find a statistically significant differences between the different urban locations. And finally, we can ask, is the physiological well-being related to the characteristics of the urban space? So the landscape architects were putting together also their parameters, what I was mentioning before, and calculating their score. And then we correlated our average physiological well-being score to the spatial parameters. And we could find out that the average of the spatial parameters that were taken into account in here, and the score that is represented on this x-axis, this includes the amount of trees in this location, the number of the points of interest, the pedestrian street, and we can see if there are more pedestrian street, more grass, more points of interest, or more trees, then also physiologically the subject feels better in this kind of environment. So we don't need to go to forest to feel ourselves good. We can be also in the city to feel ourselves good if there are also different stimulus to the subject. So this was the conclusion of our study in this project. And with this, I would also want to close my presentation. So I would like to thank you for your attention. So I went a bit over time, over 1 hour, but it's
perfect. It's perfect. Yeah. Exactly to the minute. Okay. Now there is time for a question. Maybe for questions, maybe somebody from room have some questions, or from the remote audience. If not, maybe I have one question. Because you used a PPG signal. Have you tried to get some more information from this PPG signal? For example, we had a specialist a few months ago associated with this signal and said that we can also get a brief signal from PPG. It's a low frequency signal, and if it's a raw signal, it's not filtered. We can get also this signal. Maybe it is also interesting for estimation of the stress level or something like.
Okay, I got your question. Yeah, it's very, very good question, because yes, the PPG signal amplitude is modulated with a breathing, and it is related to our nervous system and how it is working. It can be detected from the breathing from this PPG signal. Now, if you were mentioning that, perhaps we can include then also the breathing signal to the stress detection, because if we are more stressed, then also our breathing frequency is increased. So we tried actually this. We didn't take this breathing signal from the PPG signal, but we had in this device, this is like our ECG and optical signal recording device, and this enables as well to measure the transimpedance signal. So we measure the impedance signal between this white and red electrodes, so, and this impedance is then related to the oxygen volume in the lung. So we can basically get the breathing signal straightly from this transimpedance signal, and we calculated the breathing frequency, but unfortunately it didn't give any statistically significant result that we could use this for the stress assessment. I have read the studies where they have used the breathing signal as well and the breathing frequency for the stress assessment, but in this study, in this environment, we didn't see the use of it, let's say. And as well, I have mentioned in here that we use the skin conductance. The skin conductance is very reactive to the stress. However, if you want to, what we have seen is that if you want to detect the different levels of the stress, like not like is it on or off, but also the different levels between them, then we haven't seen that it is also useful. So it actually, in our last model, what we used for this well-being score calculation based on the physiological signals, we didn't have the skin conductance included there. And if you are asking you were asking also in the first part of the question that have we also tried to find out other parameters from the PPG signal, then I carried out the postdoctoral study in City University of London, and there I was trying to find the possibility how to extract the parameters that could be related to the blood flow in the artery using the PPG signal, because PPG signal is known that it is mainly related to the blood volume changes, but there are also some effects that might be related to the blood flow changes, because we have the the red blood cells, and due to the blood flow, the red blood cells also changes their orientation, which also affects the optical signal that we are registering. So if we have high blood flow, then they are oriented in the direction of the flow, and less light is more light is absorbed in the red blood cells, and if the flow is minimal or zero, then they are oriented in the other way, and the more light is passed through the artery. So it can be related to the blood flow, and also previous studies have shown in some like models and so on that it can be related to the blood flow. But yeah, it is the topic that needs more work, I would say.
Very interesting, especially the last part you said. Okay, yeah. Then maybe somebody have another questions. Anybody? Okay, then maybe it will be a time for thinking about everything, and we have contact through the email. Then I suppose that maybe some questions will appear later.
Sure. Sure.
Then thank you, Kristjan. Thank you very much. Thank you very much for a very interesting presentation. And we hope we will see again soon. Thank you very much.
Thank you. Have a nice day.
Bye-bye. Bye.